Let us now discuss the factors influencing stability of the nucleus. There are so many factors which influence stability of the nucleus. Let us discuss them one by one. The first one is mass defect. Generally, during the formation of a nucleus, from the protons and neutrons, some amount of mass is lost. During the formation of a nucleus from its constituent protons and neutrons, some amount of mass is lost. Okay. Now, this loss in mass is actually called mass defect. Mass defect can actually be given as the difference between the sum of masses of protons and neutrons, or you can say nucleons, and the actual mass of nucleus. Is mass. Okay. Sum of the masses of protons and neutrons or that of nucleons will always be greater than the actual mass of the nucleus. Because as I said, during the formation of a nucleus, from its constituent protons and neutrons, some mass is lost, of course, in the form of energy. Okay. Now, that of course can be given as delta M. It is nothing but X into MP, where X is the number of protons plus Y into Mn, where Y is the number of neutrons. So this gives us the sum of the masses of protons and neutrons. X is the number of protons, Y is the number of neutrons. Okay. Then minus the actual mass of the nucleus. Now the masses of protons and neutrons. Mass of proton can be given as 1.00785 AMU, and the mass of neutron can be given as 1.00865 AMU. Standard values. Okay. Now, one very important thing is greater the mass defect, greater is the stability, isn't it? Because if more mass is lost during the formation of a nucleus from its constituent protons and neutrons in the form of energy, the resultant thing will have a less energy, hence it will be more stable. Okay. This is about mass defect. Now the second factor that influences stability of the nucleus, that is binding energy. Now, as I said, mass defect, I mean, the difference in mass is liberated in the form of energy. As per Einstein's law of mass energy equivalence. Okay. This is, of course, called binding energy. So binding energy can be mathematically given as delta M into C square. Just like E is equal to mc square, here it is binding energy is equal to delta M, nothing but mass defect into C square. Let us take an example. See, if suppose delta M, I mean the mass defect is equal to 1 AMU. Nothing but 1.66 into 10 power minus 24 gram. Okay. In that case, binding energy can be given as 1.66 into 10 power minus 24 into 3 into 10 power 10 in CGS system. See, this can be roughly given as 1.492 into 10 power minus 3 Earth. Okay. But see, binding energy is expressed in million electron volts, or you can say mega electron volts. You know, 1 million electron volt is nothing but, see, 1 electron volt is 1.602 into 10 power minus 12 erg into million is 10 power 6. So this can be given as 1.602 into 10 power minus 6 erg. That is 1 million electron volt. Okay. Now, see, if 1.602 into 10 power minus 6 erg is 1 million electron volt, then 1.492 into 10 power minus 3 erg is how many million electron volt? Almost all 1000. That is a standard value again. That is 931.5 million electron volts. So therefore, in general, it can be given as binding energy is equal to mass defect taken in AMU multiplied by, for every AMU, 931.5 million electron volts of energy is released. So multiply that by 931.5. See, even here also it can be given as greater the binding energy, greater is the stability. Okay. Simply, greater the mass defect, greater is the binding energy, greater is the stability. Okay. It's very important. Because if more mass is lost in the form of energy, then as I said, the resultant nucleus will have lesser energy, hence is more stable. Now coming to average binding energy. The average binding energy can be given as binding energy per nucleon. That means by the total number of nucleons. Okay. Or it can be given as binding energy by mass number. Okay. Greater the mass defect, greater is the binding energy, greater is the average binding energy, and greater is the stability of the nucleus. Okay. See, when a graph is plotted between average binding energy, nothing but B bar and the mass number. It will be like this. I mean, goes on increasing with the mass number, reaches maximum, and then decrease. Okay. See, binding energy reaches maximum at about 8.7 million electron volts, which is for iron. See, as such, because iron has the maximum average binding energy, we can say that this is thermodynamically the most stable one. Energy wise. Okay. Greater the average binding energy, greater is the stability, right? Now, when the graph is seriously observed, we will find some interesting facts. See, there are certain elements or say some nuclei. See, for some nuclei, average binding energy is more than expected. Their average binding energy falls above the binding, above the average binding energy curve. They show some deviation from the regular one, especially those in which mass number is the integral multiple of four. That is in which the building blocks are helium nuclei. Having a mass number which is the integral multiple of 4. Nothing but the integral multiples of helium, which is a building block. For example, of course, helium-24, carbon-612, oxygen-816, 3 times, 4 times, like that. Building blocks are helium nuclei. Then we have neon 1020, 5 times of 4, 6 times of 4, like that. Then silicon, which is 7 times of 4. Now, all these will have their points falling above the average binding energy curve. I mean, the regular curve. Okay. Now let us see a very interesting thing called Harkins Rule. See, according to this, nuclei having even protons and even neutrons are the most stable. Then those with even protons, odd neutrons, which in turn are more stable than those with odd protons, even neutrons. And finally, those with odd protons, odd neutrons. So most stable are those with even protons and even neutrons. And the least stable are those with odd protons and odd neutrons. But why? See, in nuclei having even number of protons and even number of neutrons, stability will be more because of maximum spin pairing of protons among the protons. And neutrons among the neutrons. So this maximum spin pairing is what actually gives it the maximum stability. And in this case, of course, it is minimum. Minimum spin pairing of protons among the protons and neutrons among the neutrons. This spin pairing actually gives maximum stability. As seen in case of the stability of chromium in the topic atomic structure. Now coming to the number of such nuclei possessing even protons and even neutrons. So there are about 165 nuclei possessing even protons and even neutrons. Of course, they are the most stable. So you find large number of such nuclei in nature. Coming to even protons, odd neutrons. We have about 55 such nuclei. Then coming to odd protons, even neutrons, almost the same as the previous one, that is about 50. And finally, the least stable one, odd protons, odd neutrons, just about 4 or 5. Okay. This is about Harkins. Now, a very interesting one, that is magic numbers. So it was observed that the nuclei having a magic number of protons are stable. Even magic number of neutrons are also stable. But you know, those having both the magic number of protons as well as neutrons are the most stable. If a nucleus has magic number of protons, yes, it is stable. Even with magic number of neutrons, it is also stable. But if both are in magic numbers, then that is going to be the most stable one among given. Then what are these magic numbers? See, the magic numbers include 2, 8, 20, 28, 50, 82. Protons or and you can say both. 2, 8, 20, 28, 50, 82 and 126 neutrons. Of course, we don't have anything with 126 protons as of now in the periodic table. So 2, 8, 20, 28, 50, 82 protons are 2, 8, 20, 28, 50, 82 and 126 neutrons are, these were actually found to be the most stable nuclei. So these are called magic numbers. Okay. Let me just give you some examples. Helium-24. Magic number of protons, magic number of neutrons. O860. Again, both in magic number. Calcium-2040. Both in magic number. Lead-82-208. Yes, both are in magic number. are found to be the most stable ones than their neighboring nuclei. This is what we can say. Okay.